So this video we're going to talk about the dynamics of a simple harmonic motion. So that means we're going to be talking about the forces and the acceleration in particular. So for an oscillator, well actually let's start with for anything. The acceleration is equal to the second derivative with respect to time of x. So if you remember from the second video in the online lecture, the first one, we have a cosine omega t. Therefore, a of t is equal to negative omega squared a cosine omega t. So therefore, we can simplify that really easily to say that ax is equal to negative omega squared x. Because if you notice, this term and this term is exactly the same. And that's what's so interesting and so useful about cosine and sine functions. Now, if you remember, we're going to continue to talk about springs for this video. If you remember, the force of a spring is equal to negative k delta x or from chapter 10. And now this is a restoring force. The same goes for negative omega squared x. It's a restoring acceleration. So if I just multiply this by m, that gets me the restoring force. Restoring force always points towards equilibrium position. So when we use Newton's second law, Hooke's law, which is Hooke's law, we have spring force. So the net force of the spring force is just negative kx for the x direction if we're just talking about horizontal springs. And that's equal to max. So therefore, ax is equal to negative k over mx. So we can then start to say that the equation of motion, which is a higher order differential equation, so if we take what we have above, okay, and then this is equal to negative k over mx, this is our equation of motion. And this can't be solved by direct integration because it changes with the position. So it's a little bit more complicated than before. So this is our equation of motion for a spring. And lastly, if we take the functions from above here and we plug them in, we get, so we'll plug in negative omega squared a cosine omega t, because that's what a is equal to here. And then x is equal to x is equal to cosine omega t. We find that these cancel, and we find that omega is equal to the square root of k over m. So Again, we've found that the angular frequency of a spring does not depend on its amplitude. That is pretty significant. It's probably counterintuitive because you would think that the farther that you pull a spring back or the farther you pull your pendulum back, that the longer the period would be, when in fact that's not the case. Because if you think about it, the farther you pull a spring, the larger the force is, which means the faster it's going to move when it passes through the equilibrium point. And the faster that it's moving, the quicker it covers up that space. So it actually keeps the period the same. The only thing that matters is the stiffness of the spring, K, and the mass attached to the spring. That will change the period, but nothing else will. That's it for this and horizontal springs. I got one more video tonight. See you then.